I am Helen Arendse. I'm the IGCSE math teacher for CambriLearn. And at the moment, you are just people 1 through 5. Unfortunately, I don't know who you are until you type in the chat. So if you type a message, then it will come up with your name, and then it's a little bit more personal. We'll just give a few more moments for people to figure out how to log in, and then we'll get started with the lesson. I see we have a whole lot of shy people today. Hi, Jill. Okay. We have 7 people. This is brilliant. This is a nice big class. So let's get started. Okay, so today we are looking at IG maths, and in particular, we're going to look at sets and Venn diagrams. Hello, Luke. Okay, so the way this works is that I'm basically going to present the lesson. If you have questions, hello, Forrest, then you can put them into the chat, and then we can see how it works through in terms of if I answer them at the time or if we come back to something after the end. Okay, we're going to work through a whole lot of theory and explaining things, and then I've got some questions. And hopefully I've got lots of questions, and we'll be able to get through some nice past paper exercises towards the end of the lesson. Okay, so sets and Venn diagrams. We're going to start with actually considering inequalities. If you're not happy with inequalities, then you're really going to struggle with just understanding how a set is described. So when we talk about inequalities, we are talking about our crocodiles. Oops, wrong way around. I'm going to try and pace this slow, but I have a habit of talking fast, and I'm going to try and keep it simple. So let me know if you're struggling to follow so I can simplify it further. Otherwise, bear with me. Okay, so you should be happy with equals and not equals. Okay, when it comes to our crocodiles, we can use them to describe a whole group of numbers at once. So if we were to say, that x equals 2, x is 2 and only 2. Okay, if we were to say that x doesn't equal 2, x can be any other number, but it can't be 2. If we say that x is bigger than 2, then x has to be bigger than 2, but any number bigger than 2. We can also do x is less than 2. So it can't be 2, but it can be any number smaller. So here we can only have 2. Here we could have -1, we could have 3, we could have 10, doesn't matter. Here we could only have bigger than 2. And here we can only have smaller than 2. So the only other ones are these ones, and you can see how they're like a combination of our crocodile and our equals. Okay, so if we had x is greater than or equal to 2, it means it can be 2 or 3 or 4 or 5 or 6. So it can anything bigger than 2 or 2 itself. And the same way, if he's pointing the other way, x is less than or equal to 2. So here we can be 2, 1, 0, -1, -2, anything smaller than a 2. And a 2 itself. So once we have our inequalities sorted, then we can get into how do we actually describe a set. So, in order to describe our sets, we want to get busy with some set notation. We don't want to be writing out long, fancy sentences in maths. Okay, we want letters, simple ways to describe what we're doing and what we're looking at. So, for a set, we normally use a capital letter. So we would have something like A. So this can be our set. We would then describe our set with a pair of squiggly brackets, which are harder than you think to do on a digital pad. Okay, but then we've got to put something inside here. What is our set? So we have two different options. We can put numbers in here. Let's say A is a set of 1, 2, 3, 4, and 5. Okay, so that's all the numbers that can be in our set A. We could also say, whoa, that one is awful. Okay, our numbers 1 and 5, therefore 0 is less than x, which is less than 6. So there's another way of saying exactly the same set. We could say that 1 is included and 5 is included. So you see, when it comes to inequalities, all we're doing is describing what is in our set. Okay, so the other thing that you will see is an even fancier notation where we say x and then we have a colon and then we have a description. For example, an even number. So in this case, it's still nothing scary. All we're saying is A equals, and then we have our set with our squiggly brackets. And then we're saying that X is in our set, and we're defining him by this. So, in fact, I've made a bit of a boo-boo. This shouldn't be A. Okay, did you catch me on it? Are you just sitting there waiting to tell me it was wrong? Because we've said that A is a set of 1, 2, 3, 4, 5. So now if we're having even numbers, we need a different letter for our set. Okay, so B, we can say, is 2, 4, 6, 8. Now we're not going to sit here and list them all out. So we put ... to indicate that they carry on. So our squiggly brackets and our letters are all about just defining what's a set. What's the technical term for all these things inside the set? Okay, what is the number 5? Okay, he's an element. So 5 is an element of the set A, 4 is an element, 3 is an element, 2 and 1, they're all elements. Because element is such an important word and we use it a lot, it has its notation. It's an E, but it's rather like a C with a line in the middle. Okay, so if something is an element, you can also have something else that isn't an element. So 1, 2, 3, 4, and 5 are elements of our set, but 7, 8, and 9 are not elements. So if we want to say that it's not an element, we take our element symbol and we cross it out. So it's all very straightforward. And as you get into the notation and the sort of words and the symbols that you use in maths, you'll find there's a lot of pattern, there's a lot of repetition. And that will help you then to get more familiar with it as you go. So in this case, we can say 5 is an element of A, but for example, 7 is not an element of A. Then we have a special one, and that is the empty set. Now the empty set is nothing at all. But remember, 0 is a number and O is a letter. So we can't use either of those. So we have a special letter which looks like a little O and is crossed out. And this is the empty set. Then, so if we said, for example, we were asked to find all of the, let's say, letters in set A. Well, there aren't any. There's only numbers in A. So this is the empty set. So the next one you need to be happy with is the notation where we have n, open brackets, A, close brackets. So A we're happy with. A is the name of our set. Okay. Now these brackets are just holding him together. They're just saying he's special and he's different from this n. Because the n is our piece of interest. Okay. This n stands for number of elements. So when we say n of set A, we're saying the number of elements in set A. It's just shorthand. It's nothing fancy. So in our case here with our little set of A, the n of A equals, and we count them, 1, 2, 3, 4, 5. There are 5 elements in set A. Okay, there's one other piece of notation that we want to put in here, and that's this idea of subsets. Okay, so when it comes to subsets, we have this symbol. It's like a C who got stretched with a line underneath. And we have that same C who got stretched without a line underneath, which is a proper subset. So when it comes to these, if you think about it, sub is like smaller. It's like underneath. Okay, so it's a small set. It's a piece of our set. So we're going to take numbers out of our set and it's going to be a subset. So we could take the set of 1, 2, 4. That's a subset of A because 1, 2, and 4 are all in A. We could have 2 and 5. That's also a subset because those numbers are both in A. Even just a set of 3. 3 is in A, so it's a subset. And then, technically, 1, 2, 3, 4, 5 is also a subset because 1, 2, 3, 4, and 5 are all in A. And this is where it gets a bit silly because, I mean, 1, 2, 3, 4, and 5, why don't we just say A? Why say that's a subset of A? So that's where our notation comes in. Remember for the subset, we had this little line underneath. So now I think of that as you've got a subset or you can be equal to. So this one here, we can only call him a subset. These ones here are proper subsets. Because they don't have all of the elements. This one's a silly subset, so he's a subset or equal to. These ones are all proper subsets, just our stretchy C, because they are only some of the elements from A. Okay, so I hope it makes sense. I hope you're happy. We're going to do some more examples actually using all of this just now. So this is your moment to shout if you've got a problem with the notation or you want me to go back over something. Hopefully everybody is scribbling happily and not having problems. So let us move on to the thing that drives people nuts. Venn diagrams. Great, Luke. So breathe, calm down. Venn diagrams are not something also freaky, Okay, Venn diagrams are just a different way of looking at your sets. That's all. Okay, they are a tool. They're not a horror movie. Okay, so when we have a Venn diagram, all we are doing is making a plan so that we can see how our sets relate with each other. Jill, this comes into the IGCSE maths papers, comes into a lot of, so it's your sort of middle range of high school maths. Okay, you can also then apply it into probability and all sorts of things like that. So today I'm just covering the basics of sets and Venn diagrams. Applications would be a separate lesson. You'll get an idea of application when we work through some of the questions towards the end of the lesson. Right. So, you might have come across a Venn diagram. Maybe I should have drawn these in advance on the computer, hey? Then it would have been a bit neater. But this is real life, and you have to draw them by hand as well. So hopefully your pencils are neater than my digital pad. Right. So here we have two sets and what we call the universal set. Okay. Our universal set is another one of those ugly little letters. It's like an E, but it has a whole lot of curly bits on it. Okay. And that's the universal set. So, universal set, think of the universe, think of everything. So, everything that we're dealing with in this question would go into the universal set. And then we can have pieces which go into our smaller sets. So, let's say this is our set A and this is our set B. So, any number or value or letter that belongs in set A would belong in the A circle. Any number, letter, value belonging in the B set would go in the B circle. So you can see already there's this piece where it overlaps. Okay? And this overlap is going to be the pieces that belong in A and belong in B. So, for example, if we took our A to be 1, 2, 3, 4, 5 and our B to be even numbers, we would need 1, 2, 3, 4, 5. Because 1, 3, and 5 are in A, but they're also even numbers. Oh, sorry. I'm talking nonsense. 1, 3, and 5 are in A, and they are odd numbers. 2 and 4 are in A, but they are our even numbers. And then in B, we would have our other even numbers, 6, 8, 10. We'll stop there for now. Okay. So there's a few other bits of terminology to get busy with here. We've talked about A being this circle, okay? So the other thing we like to know about is A prime, which is the complement of A. And this just means actually what is outside A. So A is our inside. Everything in this circle, whereas the complement of A is everything inside our universal set that isn't in A. Okay, the other ones, we talked about this crossover with pieces that belong in A and belong in B. So that's an important thing. So it has a special name. It's an intersection. And we have a special symbol for that one. Looks rather like a little hill. Okay. The other thing we could say is that, sorry, there's your intersection. Okay, the piece in between where you are got A and you've got B. So the other thing that is often of interest is what we call a union. So a union, nice and easy to remember because it looks like a U, is when we join things together. So if we had A union B, it would be everything that is in A and in B all together. Okay, so union is like a U, intersection, you flip it over. And the complement is what is outside what we're talking about. So that is now basically all the theory behind sets and Venn diagrams. So let's move on to some actual questions and see how this translates into actually doing maths. So this is from the March 15 paper. So these are all IGCSE maths papers, and it is the Cambridge International Syllabus. Okay, so M15 means March 2015, and it's paper 42 and it's question 2. So what we've got here is the question actually as is from the paper. We are told that x is an integer. So remember, you're thinking just of your numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. We're told that our universal set, there's our squiggly E, is a set of, and here they're defining x for us, 1 less than or equal to x less than or equal to 10. They then give us other sets, A, B, and C. And they give us information about each of them. And what I really very strongly recommend is that you actually take the time to figure out which number is which and write it on your paper. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because remember, we have or equal to, less than or equal to, so we're including our 1 and our 10. Then A. A is a set such that x is a factor of 12. Okay, so we have 1, 2, 3, 4, and 6. 12 doesn't count because remember, our universal set is all our numbers and it only goes up to 10. Okay, so then we have to look at B, our odd numbers. So 1, 3, 5, 7, and 9. And set C is defined so that x is a prime number. So there we would have 2, 3, 5, 7. That's all of them. Yes. Okay. Then they say complete the Venn diagram to show this information. So we've got to take all those numbers we scribbled and put them in the right place. So what I like to do is I like to start in the very middle of the Venn diagram. Okay, that very middle of the Venn diagram is the numbers that occur in every single set. Okay, it occurs in A and in B and in C. So if we look through our numbers, our 3 is in A and B and C. So he has to go in the very middle. There's no other numbers that are in all of them. So let's change color. If we then go up here, we have what is in A and B. So if we look at A and B together, we have a 1 that belongs in there and nothing else. So the 1 goes in there. Next one. If we go to the left here, we're looking between A and C. So what have we got in A that we also have in C? We have a 2, and that's it. So the next one, we're going to run out of colors, I think. Between B and C, what are they sharing? Oh, this gets more interesting. They are sharing a 5 and a 7. So there we have to put the 5 and the 7. And then we have to fill in what's left. So in A, we still have a 4 and a 6 that only belong in A. In B, we have a 9 that only belongs in B. And in C, they're already all accounted for. We're not quite finished yet, though, because we have to look at the other numbers in our universal set. So I do this by elimination. We've put in 1, 2, 3, 4, 5, 6, 7. We haven't put in 8. We've put in 9, and we haven't put in 10. So 8 and 10 go outside of our circles because they're not in A, B, or C, but they are part of our universal set. Now that our Venn diagram is complete, we can go on and then complete the rest of the question. So we have a statement which says 6 is somehow related to A. So if we look at our Venn diagram, we see that 6 falls inside A. How do we say that a number is inside a set? Remember, it's called an element. So 6 is an element of A. Then they ask us, the intersection of A intersected with B intersected with C. So we have to look at who's in A intersect B intersect C. So that's the one we actually started with at the very beginning. That's our 3. So then we have to draw our squiggly brackets and just put our 3 in because he's the only one who belongs there. And now we get some fun. Now they say, what is in the set of A intersected with not in A? That's a bit odd, hey? If we look at A, we have all these numbers. If we look at not in A, the complement of A, we're looking everywhere outside of A. Well, there's no intersection between those two. So that means that we are left with the empty set. There's nothing there that falls in A and the complement of A, because it either is in A or not in A. The last piece of this one asks us to find n of B. Now remember that n means number of elements. So they don't care what numbers are in B, they just want to know how many numbers are in B. So if we go back up, in B we have 1, 2, 3, 4, 5 numbers. So our answer for this one, number in B equals 5. Because when we have the number of elements, we're just counting them. Right. There's another part to this question, and now it's using letters instead. So they have given us a full Venn diagram here, and then we've got to work with it. So use set notation to complete the statement. They tell us it's U and V, and they've got us to relate it to Z. So where do we find U and V? They're hiding here. They're inside Z, but they're not inside X. Okay, so we have to get outside of X and outside of Y just to get this little piece of Z on its own. We just want this piece of Z. Okay, so if we say that we want to be outside X and Y, we want to be outside of that. So that takes us outside of those two circles, but we don't want this W in the universal set. So we only want when this intersects with Z. And there we go. They then ask us to shade another one. So we got to work through this in stages. Okay. First we think, what is Z union Y? So Z union Y, that is these two circles together. Because remember union, we put everything together. They want X is intersecting with what is not in Z union Y. So Z union Y, then we go outside of those two circles. You can use your fingers on the paper to help you with these sorts of things. It's so much easier. So if you put one finger over the Z circle and one finger over the Y circle, you want everything else. But where that intersects X is just in this X piece. So we would only shade this one piece. And it's much easier to do this with a pencil on a piece of paper. Okay. A pause here because that's the end of our first question. Shout if you're not happy. Okay. Next question. So this one is from March 2016. It's paper 42, and this is question 3. And here we get to work with fruit. So people have been asked if they've eaten mangoes, pineapples, or bananas last week. And healthy people have all eaten all of them. Okay, they keep it nice and straightforward. M are all the people who ate mangoes. P are all the people who ate pineapples. And B are all the people who ate bananas. Then they give us a Venn diagram, but with missing information. So we're going to have to play detective a bit. They give us some information to help us. They tell us that 19 people ate mangoes. So let's write it next to our Venn diagram so it's where we can see in a useful position. So 19 ate mangoes. 6 people only ate pineapple. And 18 had 2 types of fruit. Because they then ask us to write the missing values in the Venn diagram. So let's be detectives. 19 people ate only mangoes. So we need to find our mango circle, and here it is. Okay, remember that this is a Venn diagram that shows the numbers of people in each piece. Great, Jill. So we've got 19 people who ate mangoes, and here we have 5, 4, and 7 people already. So we already have 5 plus 4 plus 7 people, which is 5 and 4 is 9 and 7 is 16 people. Okay, so if there's 19 people who have eaten mangoes, then there must be a 3 here, because 19 minus the 16 people who are already there equals 3. So 6 people have eaten only pineapples. They're very boring. But that means if they only ate pineapples, they have to be in our pineapple circle outside mangoes and bananas. So those 6 people sit here and be boring. We're then told that 18 people ate 2 types of fruit. So we think, which people ate 2 types of fruit? Well, they either ate pineapples and bananas, or they ate bananas and mangoes, or they ate mangoes and pineapples. So we can see we've already got 7 people who ate pineapple and mango, and we've got 3 people who ate mangoes and bananas. So there's 10 people already there. So 18 people ate 2 types of fruit minus the 10 people who are already there means we have 8 people who need a home, and this is where they go. So now we've done that first piece. We have filled in the 3 missing values in the Venn diagram. with our 3 numbers. We then are asked to find the total number of people that Davender asked. So, the total number of people, remember each of these numbers represents a number of people, so we've got to add them all up. So, we've got 5 plus 3 plus 4 plus 7. We have 19 people already in our mangoes. That's our 19 people. Okay, we then have, if we add in these ones in bananas, that's another 20. And then there's another 6 here. I see Luke's on the ball. We have a 1 though on the outside. Don't ever forget the 1 in the universal set. Okay, so Luke, I think we disagree. Did you forget your 1? Because I get 46. Let's just get a calculator, double check if I've done something silly or you. Definitely get 46. So I think, if I'm right, Luke, you missed. Okay, brilliant. So that is actually the perfect mistake for you to make, Luke, because it's a perfect mistake for this question is to miss that 1 sitting in the universal set. So really do take care when you're adding up numbers in a Venn diagram to get the 1 in the universal set. In this case, the boring person who didn't eat any fruit at all. So we've now got our total of 46. And then we asked again one of these n questions, the number of elements. Okay, so there they want us to find the number of elements in M intersected with P. So we have to go back to our Venn diagram and look for M intersected with P. So where does M cross over P? It's in this piece here. So we have these 2 groups of people, 7 plus 4. And 7 plus 4 gives us 11. This time Luke and I agree. Brilliant. Okay. So I know Luke is happy. Nobody else is crying yet, I hope. So let's move on to our next question. We've got about 6 minutes left before I get shouted at for going over time. So, next question, also from a March paper, this time from last year, 2017. Okay, so we have, in this case, we're told how many. We've got 20 trucks tested at a checkpoint. Goodness gracious, I'm glad I wasn't on the road with these guys. 6 trucks failed the test for brakes. 7 trucks failed the test for lights. And 9 trucks passed the test for both brakes and lights. And then they ask us to complete the Venn diagram. So, they've told us that B is failing the test for brakes. Okay, so in this B circle, there's going to be 6. But we don't know who's sitting here and who's sitting in the overlap, which is why I put it in the outside to start. 7 failed the test for lights. So there's going to be 7 trucks in lights. 9 trucks passed the test for both. So 9 trucks have to go outside here because these are the 9 trucks that should be on the road. Okay, so now we've got to think about, we've got 9 trucks who have passed everything. So we have 11 dodgy trucks. Because 20 minus 9 gives us 11. But if we look here, we've got 6 who have failed brakes and 7 who have failed lights. That's more than 11. Okay, that's 12. So how we do it is we say 6 plus 7, that's our 2 circles that equals 13, actually, not 12. Don't know where I'm getting my numbers from. Anyway, 6 plus 7 is definitely 13. We then say our 13 minus the 11 possible trucks gives us 2, which means that we have to have 2 trucks in our overlap. So 2 trucks have failed for brakes and lights, which is a bit scary. We can then say if B is 6 and 2 are here, there must be 4 trucks that failed brakes only. If L is 7 and 2 are here, there are 5 that failed lights only. So we use our overlap to find our intersection. And then we can fill in the other 2. They then ask us to find the number in the complement of B intersecting the complement of L. So, this is where those fingers come in handy again. We don't want what is in B. So we're going to use color to do this. Okay. We don't want what is in L. So pink is outside L. And we're looking for the number where those 2 intersect. So where do you have pink and green lines? It's actually here in your universal set outside your B and L. And how many we have there? We have 9. Okay, a few moments to look at that one and my beautiful pink and green lines. And then we have a few minutes just to wrap up. So, the joy of doing this on a computer is you can rewind your life. We were talking about sets and Venn diagrams today. Okay, we talked about inequalities and that importance that if you want to understand sets and Venn diagrams, you need to understand inequalities so that you can understand how the set is described. Okay. We then talked about set notation. Again, if you want to understand what's in a set, you need to understand how they're describing the set. So the importance of your squiggly brackets, your element sign, your empty set or null set, your number of elements in, how that is just n and a bracket. And then your subsets. A subset with a line underneath can be a bit dodgy, whereas a proper subset is always less numbers. We then went into Venn diagrams and we said they're just pictures, they're not horror movies. Okay? Venn diagrams are just a way of visualizing a set so that it makes it easier to work with, especially when we've got 2 or 3 sets. It's so much easier if we have a Venn diagram to see who goes where. Okay, and then we look through the questions. Putting numbers in to a set and then getting answers to questions from our Venn diagram. We looked at their Venn diagram so that we could build our own statements out of it. We looked at putting numbers of elements rather than numbers themselves into a Venn diagram. And again, finding the number of elements. And we finished off now with, again, looking at number of elements and putting them in the right places. So all the questions are basically variations on the same theme. So if you can get yourself happy with the basics, then you're set to go. Practice, practice, practice. And truly believe that Venn diagrams are not out there to make your life miserable. I'll be back again next week, same place, same time, doing something as yet to be decided. So if you, okay, right, Luke. Remember that these numbers here are the number of elements. We're saying 9 trucks. So this 9 here is the number of trucks. And in this Venn diagram, we don't have trucks A, B, C, D, and E showing. We just have the total number of trucks. So one truck is an element, and when we count the individual trucks, we get to 9. Cool, you're welcome. And have a brilliant week. Bye for now. That's great, Luke.